Okay, good morning everyone. Any questions on the project, the first project? Yes.
I had a question. Do we have to use the Newton line to let the program decide the T by C ratio, or do we have to maintain it constant, like manually?
Okay, good question. I was going to talk about that as well. So, okay, let's start off by saying this lecture 21 today. So in the last class for project 1, we talked about this possible design process, right? Or a design iteration loop. You choose a T over C max and then you go through all this. You go through all these steps and then you improve it, may change alpha star, insert a segment to whatever, right? That's just sort of the inner loop. So we did this design iteration loop in lecture 20. Right now, this is just with one selected T over C. So what you really need to do is you actually should go down, you should go and say, once you have made some progress with this loop, you go and say, so there is, because I'm not giving you a T over C max, right? The T over C max is completely open. So you do all that with one T over C max, but then you go and change the T over C max and see if you can improve it. And a lot of this is again, I said it's open-ended, right? Like I said, so this is some amount of trial and error and some amount of intuition, and in the end there is no one correct answer, or there is no sort of, I don't know if there is a best answer or something like that. There are just so many variables. This is like a real design problem. Okay. So when you select a certain T over C, you use the Newton line. So we talked about this Newt 1 G0 line. Okay, I don't have the syntax, but yeah, it's something like Newt 1 G0, 100, and then T over C max, and then 4, 1, and some clamp. I think it was 0.5 or something. We'll talk more about this line, but you use this to set this T over C max, right? So that way you're keeping T over C max same and you're changing some other things. But then that T over C max is not any kind of requirement. You have to select, I mean, it's up to you how you select the T over C max. Okay, any other questions? Okay, so we talked about Newton iteration in the last class. Basically, it's a numerical method that allows you to change some knob to achieve something, right? That's broadly what a Newton-Raphson or Newton iteration is. So today let's talk some more Okay. Without spending too much time, I want to give some background in Newton iteration. And if you've done applied aerodynamics, the other course, we have talked about this there as well, so you kind of know some of this. So this is more often called the Newton-Raphson method. It's essentially a zero finding method. So let's say we have a function f y equals f of x. The objective is find the value of x So this is a function where you put in an x and it will give you a y, right? The objective now is you want a certain y and you have to find the x that will give that y. So maybe the function is something like this. And maybe this is a function. And you want to get this value, y target. Okay, so the thing is, this is not an analytical function where you can go and solve it analytically. This could be some sort of a function that comes, it's like a function in a computer program, right? You throw in an x, it will give you a y. You throw in another x, it will give you another y, and it will keep on, you don't know its variation. And this function itself might be a very complicated computer program that does a whole bunch of calculations, and you don't even know maybe what is all there, like profile, right? You give it all these alpha stars and all these other things, and it gives out an airfoil. The inside the profile is a big black box, which is the function, and you don't know, there's all kinds of things going on there. You kind of don't even care about it. But what you want is this target. That means you have to find the x that will give you this target. In this case, it's very easy, right? You can just see and say, oh, this is x. But how do you figure it out if all you have is some kind of a computer program where you throw in an x and it will give you a y? So you always start off with the first guess, and let's say this is our first guess. We'll call this x0, x superscript 0. This is our first guess. And you throw in this x, and the program gives you the y from this. By running the computer program and doing this function analysis, it will give you the y, and this is y0, y superscript 0. Then what in Newton iteration, you have to find out which way to go. Right now, looking at this, you know that you have to decrease x to come here, right? But if the function was like this, well, if the function was like this, then you would have to increase the x. But you don't know that based on the information you have. All you know is if you give in x0, it gives you y0. So what you do is do a small perturbation, and the perturbation can be positive or negative. We'll just do a negative perturbation just because it's easier in this plot. So you do a small change to x0 and find out, does y0 decrease or increase? And then when you run the program, you get this, and so then you know that the slope of this variation is in this manner, right? If you assume this is linear, and if you assume the whole function is linear, you can say this is the variation, and in order to get y target with this linear behavior, assumed linear behavior, the Newton method will say, oh, if I assume linearity, then this will be the x that I have to go to. So this becomes the next guess, a better guess, right? So it's like a second guess or something. Second estimate, okay? So, and when you now put this x1 into the function, it will give you a y value, which is y1. So at the end of the first iteration, you put in x1 and you get a y1, and then you do the same thing. You make a small perturbation, find the slope, and the next slope will take you here. This is x2. At the end of the second iteration, this is x2, this is y2. And all the time you see that you're coming closer and closer to y target. So, you know, in one more step or two more steps, you'll actually come right here within a certain tolerance, a defined tolerance. You can come and say that will be the x that gives me y target. So this is x solution. And that's how Newton-Raphson works. So that's essentially how this, you know, numerically this method will change the knob to achieve something. But this is all fine when you have well-behaved functions. There are many functions that are not going to be well-behaved, and that's when you need to do some special things. And this has all been well known for a long time. So when you have a non-well-behaved function, then maybe your function looks like this. And you don't know, right? You don't have a picture of this function. It's all numerical. So if you start off with x0, and this is y0, and now you find the slope by doing a small perturbation and all that, and the slope will take you here. And this becomes x1. So at the end of the first iteration, you have x1, and let's say this is the y. I should have done that. Okay, let's call this the y target. So this is what we want. This is the solution. Okay. So now x1 is here. Again, you take a slope, and this slope will kick you all the way here. And this is x2. This is x2, and this is x1, and this is y1. Now we have x2, and this is y1. Right? Again, you take a slope, and you can see this is a sort of function where if you make a guess here, you'll actually be going round and round, never getting to this point. This is the point where we want to come. So what you do in such circumstances, and again, you don't have this picture in front of you to say this is what I have to do. So you have to see from the behavior of how your iteration is going and then deduce saying, oh, this is what is happening. You have to form a mental picture pretty much. So what you say is, okay, so if Newton method, after the first guess, it's asking me to go all the way here. I'm not going to go all the way there. I'm going to go only a little bit portion of that. So instead of going, and that's called clamp. So with a clamp, clamp is just the word used in Profile. In some other methods, they'll call it damping or something. So clamp is essentially a maximum in delta x. So if Newton iteration takes you from here all the way here, and if the clamp is so much, and this is just a guess, so when the functions don't behave well, you give a clamp. So even though Newton iteration says go all the way here, you go only by clamp amount. Right, and then you come here. Now this becomes your x1. Maybe I'll put that in red. Right, then you take a slope again, and this slope also takes you all the way here, but you go only by clamp amount, and this becomes x2. And then same thing, you do a slope again, and this slope will take you here, but you go only by a clamp amount. Right, and then this will come here, and you're getting very close to the target now. So there are some situations in which you have to use a clamp or a damping. You essentially damp the Newton iteration so that it takes care of non-well-behaved functions like this, and that's when we had that extra term called clamp, which was there in the Newton method. We'll talk about it again now, so I think it was there in that example. And so some of this has already been figured out for most Newton lines. So when I give you an example profile file with a Newton line, if it has a clamp value, just leave it like that. The disadvantage of using clamp when you have a well-behaved function is just it'll take more number of iterations to converge. But usually, unless it's a very complicated design case, it doesn't matter at all. You won't even notice. Okay. Any questions here? Yes.
If the y target is a negative value, how the iteration will go?
It'll still work automatically. I'll show you in a minute. One second. So in this iteration or in the simple one? In this one, okay. Let's say the y target is here, right? I'll draw in a new sheet of paper. Okay. Let's say this is y target. So this is the x solution. And you start here. So this is x0, y0, and you numerically calculate the slope, and it comes here. In this case, the way I drew it, it works easily. This will become x1, this will become y1, and then you take the slope, and now the slope is telling you to go this way. It'll actually go here, and this becomes x2, y2, and then you take the slope again, and it just happens to come directly. Y target can be positive or negative, it actually doesn't matter. The Newton iteration will automatically take all the differences correctly and go to the solution. You might still need the clamp. So, all right. Any more questions? So big challenge in these things is you have to tell the code how to give, what knob to use and what value to achieve for what variable, right? You might have to say, use alpha star on the upper surface and get me a thickness of, 0.12. Use the alpha stars on the lower surface and get me a camber of 0.01, something like that. So you have to be able to tell profile, use this knob, get me this, use that knob, get me this. And so there is a syntax that Professor Selig has come up with. He's the one who wrote Profile, right? So he came up with the syntax and it actually works really well. It takes a little while to understand, but once you figure it out, it's very powerful. Okay, so let's talk a little bit about this. So here's the syntax and all the options for the Newt1 G0 line. So remember, this is 0, not O. So you say Newt1 G0, and then there is 1, 2, 3, 4, 5. 5 options. 5 arguments. The last one is optional. This is when if you think the Newton iteration needs damping, you put a clamp. So basically you have to put some numbers for all this, and with that profile, the code in Fortran code has been written so that if this number is something, it will go and do something. If this number is something else, it will go and do something else, like that. And there is a key for all this. So Newt1 G0 IFTP1, this means, this dot means it's a single number. So IFTP1 basically says Newton function type. In other words, what do you want to specify? Example may be thickness. If you have to tell profile, I want to control thickness, you have to choose a certain key for this. For example, if you put 102 instead of IFTP1, that means you're telling profile, with this Newton line, I want to control thickness. And there are all these options, right? There are some more too, but these are the main ones. I mean, unlikely you'll need anything else. Even this is too much. So if you put 100, you control something called KS. If you put 101, you want a certain pitching moment. 102 is thickness, 103 is alpha 0 lift, and so on. FNewt1 means this is the value I want for this parameter. So yeah, so the desired value for the parameter that is specified in IFTP1. So 0.12 means, let's say you select 102 for IFTP1 and then 0.12 for FNewt1. That means you're telling profile, I want a T over C max and the value I want is 0.12 or 12% thickness. So pretty straightforward. Okay. Then let's see what these two do. These two are used together to say what knob you want to select. Right? This is basically saying this is what I want to achieve. Then you have to say use this knob and adjust it, right? Some knob, whatever it is. So ITP1 and ITP2, which is this part, right? These two numbers, 1, 2, third and fourth number, they are used together to identify the input variables for the iteration. And clamp1 is the optional, it's an optional argument. Sometimes you use it, sometimes you don't. Even in my file, sometimes you will have that last argument, sometimes it will be missing. It just means from experience that particular file didn't need it. right? I didn't have to use clamp, so I didn't use clamp. It's an optional step limit for the iteration. This is basically what I talked about in the non-well-behaved function. So now for these two, there is a table that tells you how to select the numbers. So these are the main options for the input variables ITP1 and ITP2. So if ITP1 is number 1, that means you're using the knob phi. Remember, phi is the angular coordinate of all the segments. So you can vary one segment's phi, or you can vary all the upper surface segment phi, all the lower surface segment phis, or everything, or just the leading edge, and do some things like that, right? So if you put a single number like I, that means it will vary phi I. That is vary phi for the end of the segment number I. So if it's 4, then it will go and vary fourth segment phi. If you put 100, it will vary phi for all the upper surface segments except phi I leading edge. So let me try to draw this. I'll put a circle here. So this is 1, 2, 3, 4, 5, 6, and 7. Let's say there are 7 segments. It'll be 1, 2, 3, 4, 5, 6, and 7. Right, so basically 100 will vary everything except the leading edge. So this is 100 will vary these 3 phis. All of them together, they'll all, like, it'll add, let's say 1 to all of them, they'll all move by 1. If you add 2, they'll all move by 2, and so on. ITP2 will vary everything for the lower surface segments except phi leading edge. So these two will be 200. Of course, this won't move, right? This is always 60. 300 will add to this and subtract to this. 400 will add to both. It'll add here and it'll add here. So 300 will go, if you add 1 degree to all the top, it'll subtract 1 degree from all the bottom. 400 will add, it'll add 1 degree to everything, things like that. And 800 will move all of them all the way from 1 to 6. That's what vary all the segments, upper surface, lower surface, and I leading edge. Okay, so that's what happens with 1 and any of these numbers. Now 4 is V level. Let's come to this in a couple of pages. This is a little harder to talk about. Let's go to 6. 6 is alpha star. This is what we have been talking about with the symmetric airfoil example in the past couple of classes. So if you put ITP as 6, profile will say, oh, I have to go and change alpha star, but which alpha star to use? That's again the same as this. If you put some number like 1 or 2 or 3, that means it will vary that alpha star. If you put 100, it will vary all of the upper surface segments. So 100 will select all of these. So alpha star is for this region, right? 200 will be all the lower surface alpha stars, all the lower surface segments. So if you have 5, 6, 7, this is 200. 300 is the same as earlier. It will add to all the upper surface and it will subtract to all the lower surface. 400 will be add to both upper surface and lower surface. So for example, in the symmetric airfoil, when you wanted to adjust thickness, you add something to the upper surface, but because it's symmetric, the lower surface is all exactly negative, right? So you have to subtract from that. So that's why we selected 6 and 300 in the Newton iteration. Yeah, so I think I don't have that page today. Oh, wait. So in the first page in today, actually I wrote 4 and 1, that's wrong. No, so this is 102. Sorry, yeah, this is 102. So you need 102, thickness max 6. 6 is for alpha star and 300. Right, so let's unpack this Newton line. Okay, I'm just going to write it here. No, I'll write it in a new page. So you'll say Newt 1 G0, and we know that okay. Where did I put that page? Yeah. We know that 102 is thickness max. So you put 102 and you want a 0.12 thickness. And then we saw this, right? By changing alpha star is the best control for thickness. So you have to select alpha star 6, and then anytime you add to the upper surface, you have to subtract to the lower surface. That's how it will be symmetric. So you do 6 and 300. 6, 300, and then if you want a clamp, you can put 0.5. That means the alpha stars will only change by 0.5 every time in the iteration, and so it will converge even if it's a difficult iteration. Okay, does that make sense? Questions? And then if you put IDES, that means basically here you're saying this is the knob and I want to achieve this thickness. IDES means now go do the iteration. Okay, let me get my pages organized. I got them all mixed up. So 21. So 21-4. No, it's 21-4. Okay, so it turns out that there is this thing called KS. There is this parameter in conformal mapping in Profoil called KS. And that's what is there in this table. This option number 100 is KS. And KS is basically a trailing edge shape parameter. Think of it as some parameter that controls the trailing edge shape. There is no exact sort of definition for this, like thickness max is a very clear definition, right? It's the maximum thickness. This is somewhat of a fuzzy parameter. There's no proper way to define it. Think of it as something like the thickness in the vicinity of the trailing edge. That's what this is. It's something that controls the general appearance of the thickness in the vicinity of the trailing edge. And this Ks needs to be between between 0.0 and 0.8. This is just based on experience that this is the usual range, unless there's some weird airfoil design condition, usually 0.8 to 0 to 0.8. So, and if you don't do KS first, the airfoil starts looking really weird and bad. So pretty much the first iteration you have to use is the KS in almost any airfoil. It's like a, based on experience, people who have done conformal mapping with this kind of method have figured out that the first thing you do, get KS into some reasonable range and then work with everything else. So essential that a reasonable value of KS be achieved, and the good thing is Newton iteration will take care of it for you. You don't have to mess with it at all. So that is usually the first Newton iteration. So even in the profile example files, which I'll show now. So in all the profile input files, you'll find some line like this. This basically says adjust KS. This 100 and 0.3 means if you go to this, IFTP1 of 100 means KS, and then the next number is what do you want for KS. Right? It should be between 0 and 0.8. This means achieve a desired KS of 0.3. That's what you're setting this Newton iteration to go and achieve this. And 4.1, what is 4.1? 4.1 means 4 is V level and 1 means I. That's the segment endpoint. So you're saying go and adjust the velocity level of segment endpoint 1 and use that as a knob and get me a KS of 0.3. So this is V level, essentially the V value of end of segment. EOS is end of segment 1. So let's see what that means. So when you plot the velocity distribution, let's say you have some velocity distribution like this, and this is the end of segment 1. So EOS means end of segment, or segment endpoint basically. So this velocity value, so the alpha at which this velocity distribution is plotted is alpha equals alpha star of first segment. So let's say alpha star of the first segment is 4. So when you plot this distribution at alpha equals 4, this value, the velocity value, this is V level of V level 1, VLEV1. So people who have done this conformal mapping figured out that if you want to adjust Ks, the best variable to change is this velocity. So you go on, you're telling Profile, use the velocity level of 1 and get me a Ks of 0.3. And once you set this Newton iteration and it works, then you don't have to worry about it. It'll always keep doing it. So it's nice. And then if you want to say, let me change Ks, maybe instead of 0.3, I'll use 0.6. You just change this number, run it again and see what happens, right? But basically it'll keep on changing this to get you this value. So that is the first Newton line that you use in any airfoil, whether it's symmetric or cambered. So in a cambered airfoil, also the first line is usually this and this. Let's look at this line. So Newt 1 G0, 100 and 0.5. That means achieve Ks equals 0.5. And here I've put 1 and 800. And so in a cambered airfoil, you do things differently. The knob that you use is phi for all segments. Okay, so in symmetric airfoil, you vary V level. This is again, people have found this by experience. So we are just sort of inheriting all that information and using it. But in a cambered airfoil, the best way to achieve a certain Ks is to move all the phis. All the phis are the leading edge phi. So instead of this, or one can use phi for ILE. That is, in that case, the Newton line will be Newt 1 G0, 100, 0.5, 1, and then this might be like 5 or something. This should be same as the ILE value. So for example, if you have an airfoil and if the ILE segment is 5, it will be 4, 3, 2, 1, and then maybe 6 and 7 and 8. So this is ILE, right? So again, people found out from experience that changing the phi of this will, in a cambered airfoil, will give you control over Ks. So okay, so let's talk some more about this. So usually between 0.0 and 0.8. For symmetric, use V level of the first segment as the knob. So for that you will do Newt 1 G0, 100, 0.3, 4 and 1 IDES. Right? For cambered, use phi for ILE or phi for all segments as the knob. You know what I mean by knob, right? As the control, basically. So there you'll say Newt1 G0, 100, and let's say it's 0.5. You know, this can be 0.3, 0.5, whatever, something like that. And then you'll say 1 and 5. If 5 is your leading edge segment. No, this could be 13. If this is 13, then this will have to be 13. Or it can be same thing, Newt1 G0, 100, 0.5, 1 and 800. And then IDs. So there's a reason for 800. In some situations it's helpful, and the kind of situations are really the correct control, the correct knob is 1 and ILE. Okay, but the problem with ILE is, let's say you have a segment endpoint here, segment endpoint here, segment endpoint here, and this is ILE, which can be 5 or 13 or whatever, something like that. This is ILE minus 1. This is a phi, right? This is phi controls this. This is angular. So if you ask Newton iteration to move this around, Newton iteration can say, okay, I need to move this phi ILE this way, this way, this way, and then it'll go and come here, and then it'll cross over. Newton iteration is just a mathematical method. It's just going and changing. It doesn't know anything about what's happening inside. So when this comes and crosses over here, or when it comes this way and crosses over here, Newton or profile, the conformal mapping method will crash. The math won't work out, so the program will not be able to run properly, and it will crash. It will give you a weird error message. So that's what happens if you move just this. So in some situations, the workaround is, hey, I just don't want to move this. I want to move all of them. Let me move all of them. Let me slide all of them back and forth and achieve KS. So if you slide all of them, how many ever you have, then if you slide all of them back and forth the same amount, then this will never cross, and that's the 800 option. Okay, does that make sense? So in some situations, the 800 option may not be a great idea. It'll probably work out, but sometimes you want to keep this at a certain X over C location, and then maybe the 800 is not the best option. But I think for you, it won't matter. The other problem with using ILE is, if you put 1 and 5, that means you're saying change phi of the fifth segment. It has to be the same as the ILE, right? Later on, you go and insert some segments in the upper surface by changing the foil lines, and you make ILE as 7. You have to come and remember to make this 7. So this has to be always the same as ILE. If we were to make some changes to profile, we should probably introduce an option saying, 900 means ILE, then we don't have to keep on changing every time we change ILE. But right now it's like this. Okay, so cambered airfoil, this is the first iteration. Second iteration is usually pitching moment. You almost always have to get pitching moment correct, otherwise the airfoil will again just look very strange and unreasonable. So pitching moment, the Newt line is IFTP1 is 101, and then the desired value of the pitching moment. So here you say desired CM0, which is same as CMAC of minus 0.09. That's a reasonable pitching moment for an airfoil. I mean, so if you can vary this number and it'll change the pitching moment and it'll adjust the velocity distribution. Pretty much the only way to see that is to go and change this number and see if it looks nice. Sometimes your design might say, I don't want a pitching moment more than some amount. So then this number cannot exceed that. And here, the knob is V level of 1. Remember, in a symmetric airfoil, we used V level of 1 to achieve Ks. Right, in the previous page for a symmetric airfoil, this is a symmetric airfoil. V level of 1 is used to achieve Ks. Here, V level of 1 is used to achieve certain pitching moment. Again, don't worry too much about this. This is how people have found this is effective, so that's a good Newton line. And these will be there in your sample files that I give you. So you don't have to think through it too much. So why can't you use phi of the leading edge to achieve Ks in a symmetric airfoil? Right? Remember, in a cambered airfoil, we use phi for I leading edge to achieve a certain Ks. Whereas in the symmetric, we use V level of 1. Why can't you use phi of I leading edge in the symmetric as well to achieve a certain Ks?
You would duplicate the point and they would overlap.
I mean, you might be close, but what is phi of I leading edge for a cambered airfoil? 30. It has to be 30, right? There's no choice. That's because it's a symmetric airfoil, the I leading edge has to be exactly halfway around the circle, which in these coordinates is 30. That can't be moved. That's why you can't use that as a variable. Because if you move it, you're not talking about symmetric airfoil anymore. Okay, so some of this will only start making sense when you start messing around with profile and go use it. Okay, the other thing then is I should point out that these options, so 101 is pitching moment. What is pitching moment for a symmetric airfoil? 0. Like that, alpha 0 lift. What is alpha 0 lift for a symmetric airfoil? 0. So you can't use these options for symmetric, right? I mean, by definition, if you're doing a symmetric airfoil, it's meaningless to say, hey, set this to 0.1 or something. It won't, it's nonsensical. So this and this, okay. There is one more Newton line which you might use. This is probably in the project too.
I want to ask, can you use the same knob to control different things?
Awesome, that's a good question. That's an excellent question. So the question is, can you use the same knob to control two different things? So this morning I was trying to think of, I forgot to talk about that. Good thing you asked me. I was trying to think of how to explain this, but let's say you have a monitor or, let's say you have a computer with a speaker. So you want to adjust the volume when you're listening to music, and you have a knob for brightness, right? But if somebody put the same knob for both, it won't work, right? If you use the same, there's only one knob, and that knob controls brightness. It also controls volume. I mean, it's kind of, it's strange. If you control one thing, the other one will also change. So like that in Newton iteration also, once you select a knob for certain something, like thickness, you can't use the same knob for something else, like Ks or camber or alpha zero lift or something. In fact, the Newton iteration will crash. I don't know, the error, it will give out an error message, but I don't know if the error message might be pretty cryptic. But just remember, if you select one knob, like alpha stars on the upper surface, if you select it for thickness, you can't select alpha stars on the upper surface for camber. You can select alpha stars on the lower surface for camber, but one knob can only control one thing. Okay, although it might have a secondary effect on something else, right? So let's say you have one knob and you're going to set it for thickness. But it turns out when you change thickness, indirectly it's affecting Ks. So, but then if you have another knob like V level of 1 to control Ks, so even though when you change thickness Ks is altering, this knob will then go and adjust to keep Ks wherever you want. So that's the beautiful thing. Once you have Newton iteration working well, not just in profile, even in some other research, and this is called multi-dimensional Newton iteration. It's like multiple knobs each controlling one thing, but they all have side effects. So when you change one knob, you're controlling this, but something else is changing. Then the other knob will automatically keep moving to keep that in place, and the third knob will move to come. If it converges, it works so beautifully. It's like magic. Okay, so there is one more Newton iteration. This is a little bit more complicated. You will use this only in project 2. I mean, you could use it in project 1, but I don't think there is a need to. So suppose you want to set the extent of laminar flow or something like that. Suppose you want to design some airfoil where you want favorable gradient till here. Let's say you want favorable gradient till 50% chord. And let's say this is the transition ramp. And maybe there are more segments here. You could even say, I want this to be at 60% chord, and 50 to 60 is a transition ramp, and maybe these things are at, let's say this is at 53, and this is at 57, something like that. And let's say you want to keep them there. The problem is anytime you change anything, this will move around. Because in profile you're only setting phi, and phi might be, I don't know, something like 15 or something. If you set phi as 15, the mapping will move that to some other x location. The phi of 15 may correspond to 45% chord for some variables, 48% chord. So every time you change something, that x value will move. So suppose you want to, so there is a Newton line. To fix the x over c value of one or more segment endpoints. So what variable do you think you should use when you want to fix the x over c value? Yeah, you use the phi for this, right? If you set a phi of 45, maybe this will be, instead of 50, it will be at 47. So if you change the phi a little bit, this will move around, right? So the thing is, you don't want to do that by hand. You can set up a Newton line for this, and this is a syntax. This Newton line is used when you want to set the x over c of a segment endpoint by varying the phi for that segment endpoint. It's a little bit more complicated, but this is how it goes. So you use this Newt1 S0. Okay, S means segment. So it's just the syntax. Don't worry too much. There are many options in profile that we are not even talking about. They're kind of advanced things, and they're sometimes used for very, very special situations. So these are the main ones anyway. Newt1 S0, IFTP1, you have to use 400. JSeg IX1, which is basically profile speak for segment number of the endpoint which you want to set this X over C value for. Essentially, if segment endpoint 3 you want it to be at 50%, you will say this is number 3. LLBOS is basically an option in profile where it allows you to select either beginning of segment or end of segment. We always want to use end of segment, so this will be 0. FNewt1 is what value of X over C you want. ITP1 is 1 because you want to change phi. So ITP1 is phi. And then I is the segment end number in the segment that you want, right? So ITP2 is same as JSeg IX1, which is this. So if you say, I want the end of segment 4 to be at 50%, then this will be your telling profile, this one. I want the X over C of segment endpoint 4 to be something, which is this. And now go change the phi for that segment endpoint. So this will also be, ITP2 will be 4. Clamp is some value that works well, usually 1 works well. So for example, to set the X over C of endpoint of segment number 2 to 0.6, we'll say Newt1 S0 4 2 means segment endpoint 2, 0 is just hardwire it to 0, 0.6 is the X over C that you want, and then change phi. 1 means change phi. This is wrong, right? I think I made a mistake here. That should be 2. And then 1 is clamp. Let's see. Okay. Okay, does this make sense? So this is maybe useful in project 1, project 2. So keep this in mind for future. All right. So let me make a mention of one more thing. So here is this page we talked about for a cambered airfoil. Usually the first Newton iteration, you vary phi of either the leading edge or all the segments to achieve a certain KS. You vary V level of 1 to achieve a certain pitching moment. And when you do, first when profile sees this, it says, oh, that's the Newton iteration. You do IDES. That means it will go and do the Newton iteration, set it. Then when it sees this, it says, oh, this guy wants me to change V level to achieve a certain pitching moment. So it sets that iteration. And now when it does IDES, it will not only do this, it will also keep this knob adjusted to get the first iteration always satisfied. So that's when it does a multi-dimensional Newton iteration, and I can very quickly explain how that works. So we had Newt1 G0 for KS by adjusting phi phi of I leading edge or phi of 800, and then IDES. Then we had another Newton line for CM0, which is pitching moment, by adjusting velocity of in point of segment 1 IDES. So the variable here, or which is the control, think of it as the knob or the control. The way you have selected it is you want to control a certain target parameter, right? So you select phi of I leading edge to control Ks. You select V of 1 to control pitching moment. And when it comes here, anytime you adjust this, this will also change slightly. So it will be adjusting both knobs all the time to make sure this is achieved and this is achieved. And the way, if you ever want to look into this for something in your own research later on, the way this is done is by calculating this Jacobian. Basically it will calculate these partial derivatives numerically. So it will calculate partial derivative of Ks with respect to phi I leading edge, and then it will calculate Ks with respect to V of 1, and then it will calculate pitching moment with respect to phi of I leading edge and pitching moment with respect to V of 1. This is just kind of extra information. You don't really need this to use Profile, but this is really cool stuff. So the diagonal terms are the dominant controls. Right here Ks is controlling, or phi leading edge is controlling Ks, V1 is controlling pitching moment. These are like the side effects, let's say. Anything off diagonal is side effects, but because you're calculating this whole Jacobian, it predicts that, hey, I'm going to move this knob to change this, but there will be a side effect of a little bit on this one. So I have to move this knob by some amount to control the side effect. And on top of that, this knob I have to move to achieve something, but this knob has a side effect here. So, it's really cool. It's like, I don't know, have you all studied anything like this in math? You've probably done some iterative numerical methods or something. From my experience though, when you learn this in a math class, it's just like, whatever, they're teaching me this strange thing, and you do all these matrices and you juggle this and put this there, and something in the end you get something, and you don't even know why you're doing it. It's only when you go and implement it in engineering for your own project or something, then you say, oh wow, that's what it is for. So I kind of try to bring this out in classes. Okay, we have about 5 minutes. So I want to just show some of these things, and I think the beginning of next class we'll be able to wrap this up. That'll be the end of Profile. But by the end of today you should have everything you need for the symmetric airfoil for project 1 anyway. If MATLAB finishes booting up. I should have started this earlier. Oh my God, this is slow. Okay. So I'm going to just load up the symmetric airfoil demo. Let's just load up the latest one we did in the last class, which was demo number 7. I mean, I'm just choosing something at random. So I've selected it. Let's go and plot all these things. And this is the profile input file, and this is the profile dump file. Why does it have only 4? Oh, right, okay. This is symmetric airfoil. So there are 8 segments, but there will be only 4 necessary foil lines, right? So if you go to the dump file has the converged distribution. So the profile input file has a V level, your initial guess, right, is V level of 0.9401 something. Actually that number doesn't matter because the Newton iteration will go and change it anyway. And the first Newton iteration says, hey, get me a Ks of 0.3 by changing V level of 1. So basically it's saying, I'm giving you a guess now, you're saying I'm giving you a guess of this, go alter it as needed to set a Ks. And when the Newton iteration converged, this number would have got altered to 0.9769. So let's do this. Let's just put one alpha SP of 2 and let me run it once. Okay, just to keep things simple, I'm keeping one angle of attack at which I'm plotting the velocity distribution, and I'm going to turn off this Newton iteration. I'm going to comment that out. So this time when it runs, it's not setting Ks, it'll just use this one V level, and that might end up turning pretty weird, but we'll see what happens. See, look at this, the airfoil is pretty strange looking. And actually if you go and plot the velocity distribution, let's turn off this also. No, Control S. It crashed. I mean, it didn't crash, but it gave out an error message. So I'm going to copy these foil lines. Okay, I'm not going to comment out this Newton iteration. So the alpha star for the first segment is like minus 12.6, right? So if I plot the alpha, if I plot for that alpha, like minus 12.617 something, you'll actually see that the V level for 1, this is, this is lower surface and this is upper surface for that alpha star. This is actually 0.9401, actually it will be that, right? And that is the value I gave here. So this V level actually controls the velocity at this end point of segment 1 at its alpha star. Of course, at some other alpha it will be different, right? Now Newton iteration will go and change it. This Newton iteration, which I commented out, will change it to something else to achieve a certain Ks. And the minute you do that, this weird looking airfoil will become pretty normal. Okay, now if you go in this case, these two are both active, so it's on top of that it'll also get a certain thickness. Phi S is basically the phi for these two segment. This is not really a segment endpoint. This is really some kind of a control over the trailing edge shape. So sometimes you just have to move that around to see what happens. So instead of 8.5, I can say 5.5. But when you change this in a symmetric airfoil, on the upper surface, whatever you do, that has to be mirrored on the lower surface. So 5.5, so 60 minus 5.5 will be 54.5? 5.5? Yeah, 54.5. And actually, I think Profile doesn't even read that. If it knows it's a symmetric airfoil, it'll just read this. So you can see that this has moved. This white point has moved here. In this case, it's only changed the airfoil shape a tiny bit. So that's sometimes the only way to figure that out is to change it, but just don't make it cross over the segment endpoint 1. Like, you know, this X thing, that is phi S, that has to be between the start of the airfoil and the first segment. So if you try to put it on this side, it won't work. So it's basically a way to control the velocity distribution shape in the first segment. And like that, recovery is another parameter that controls the velocity distribution in the first segment. So basically the only way to figure out what that does is to go and change it. So maybe let's try 0.5. I'll get some more notes on this in the next class, but we'll do this and stop today. So 0.5, on a symmetric airfoil, both should be the same. So basically the change was very small, really can't even notice. But you can take it all the way to 10.5, for example. 10.5 will become 49.5, right? So if I make phi S of 10.5, then you'll probably get a much bigger change. Maybe not. So, you know, the changes are really small. So quickly, that's what is phi S and recovery REC lines. Basically try, you change them a little bit and see what happens, and then if you like it, move with it or keep it wherever it was. All right, so I'll see you on Thursday. Thanks.